The problem statement from GATE Physics 2015 paper reads as follows. In the given circuit, if the open loop gain A equal to 10 to the power 5, the feedback configuration and the closed loop gain AF are. We are given a circuit with an op amp and we need to find out what's the feedback configuration and the closed loop gain. Before we start a problem with regards to op amp, we first ask ourselves a few questions. First, is this an ideal op amp? Now, let's check the question. The question is silent whether the op amp is ideal or not. If nothing is given, we'll assume that it is ideal. If it is non-ideal, the question has to say it's non-ideal. Second, is there a feedback? Well, the question itself mentions its feedback configuration. So yes, there is a feedback, but we'll again verify. So this is the output node V0 and this is the inverting input. Now, this output node V0 is being fed to the input node through this resistor of 9K. We call this feedback resistor. We call it RF. So yes, there is a feedback. What kind of feedback? Positive or negative? It's a negative feedback. Why is it a negative feedback? Because the feedback is being routed through the inverting terminal, the negative terminal, hence a negative feedback. Now, so this is the summary. Open loop gain is given. We need to find the closed loop gain. Now, before we begin, since this is an ideal op amp, so the current flowing inside would be 0. Now, we'll observe an interesting thing here. Now remember that there was an Rn in the non-ideal case. So I'll write this Ohm's law across this Rn. So I can write V plus minus V minus equal to Rn times I. Note that no current is flowing inside this op amp. So I is 0. So I get V plus minus V minus equal to 0. This implies V plus equal to V minus. This condition is known as virtual short. Why are we calling it short? Because both the input terminals are at the same potential. Why virtual? Because they're not actual shorted using a wire. It's as if it appears as if they are shorted. So it's called a virtual short and we denote it by a dotted line between these two terminals. Okay, so now let's try to solve this problem. Let's assume that the voltage here is Vx. Now due to this virtual short, so V plus is Vi and this is Vx. So this is our first expression, right? Now note that since no current is flowing through here, so all the current I that's flowing through the 9K resistor must flow through this resistor because no current can flow here. So if you apply KCL here, if current I is coming in this direction and no current is going in this direction, so all the current that's flowing through this node has to flow through 1K resistor. Okay, so now I'll write Ohm's law across this. Let's call this resistor R across R. Okay, so I'll write Vx minus 0, that's the voltage drop across this resistor, equal to I, the current flowing through the resistor, times R. So I get I equal to Vx over R. Let's call this expression 2. Now let's write Ohm's law across RF. So the potential drop across RF is V0 minus, so V0 minus Vx. V0 minus Vx equal to current flowing through this RF is I times RF. I'll get I equal to V0 minus Vx over RF. Okay, now since I have the expression for current from 2 and 3, so I can write from 2 equal to 3. What I'll get is Vx over R equal to V0 minus Vx over RF. So I'll take RF on this side, so it will be V0 equal to Vx 1 plus RF over R. Vx is nothing but Vin, so this is Vin 1 plus Rf over R, and we get V naught upon V in as 1 plus Rf upon R. I'll simply plug in the values. Rf is 9k and R is 1k, so k and k gets cancelled. 1 plus 9 is 10. So what we get, the closed loop gain is 10. Note that this is independent of the open loop gain. It only depends on the RF, the feedback resistor, and the resistor that's being used to dump the current, R. So it's completely independent of open loop gain. So anyways, we get the closed loop gain as 10. So let's see. So this is not correct. So okay, so these three options, all of them has option has AF as 10. Now the next thing we need to find the feedback configuration. Now the problem asks us to analyze a non-inverting negative feedback amplifier. So we have drawn a circuit for this here, where the feedback circuit consists of this feedback resistor R2, and R2 and R1 combined provide a pathway for the current to flow from the output to the ground. The input is Vin, which is being provided to the non-inverting terminal here, and we can assume that the open loop gain for this amplifier is capital A. Now note that this circuit can be represented using this generic the feedback circuit that we usually encounter. So we're doing nothing here. So the input is still V in here. The open loop gain is still A, which is being represented here. The only thing that we have changed is that this circuitry in your bottom half, comprising of R1 and R2 resistors, is now being represented by a singular factor named B, the feedback factor, you can call it, feedback gain. So but the other parameters remain the same. For instance, let's see the value of V sum here. So the value of V sum, so let's first calculate the value of this signal here. This signal would be B times V out, and consequently V sum would be V in minus, note the minus sign here, minus B times V out. Correct. Now let's analyze this circuit again. So what we can say, so let's again see the input that is here. So let's call this potential difference VE. So VE we can write as V in, which is the signal here, minus, note that this is V out, and this is a potential divider. So the potential here would be V out times R1 over R1 plus R2. Now note that this is the input to the input here, what we're calling V sum, and VE are effectively the same. So VE is nothing but V sum. Now if we compare these two parameters, we can clearly say that A is the open loop gain for both, which is pretty evident, self-evident. However, the factor B, which we saw the feedback factor here, by comparison we can say that the feedback factor B is nothing but R1 over R1 plus R2. So this is the information that we gain, and we have established that this circuit, the non-inverting negative feedback circuit, can be represented using a generic feedback configuration. Now let's talk a bit more about this feedback configuration. Now note that the output, we are shunting the output, so we are effectively taking whatever the voltage is and feeding it to our feedback network here. So this configuration where the output is fed, where the output voltage is fed to the feedback network, is known as the shunt configuration. So on the output side we have a shunt configuration because it's sort of a parallel. So whatever output voltage we are getting, we are directly feeding it to the feedback network. However, on the input side to this operational amplifier, we are putting the output voltage in series. Note that we are not directly feeding the result of this feedback network to our operational amplifier. No, we are providing the result of this feedback network in series to another signal V in here. So note this formula, V in minus VB out. So we are doing effectively, we are adding or subtracting the two voltages in this case, which means that on the left side, on the input side of this op amp, we have a configuration known as series configuration. Why series? Because the voltages are being added or subtracted, because it's a negative sign, it's a negative feedback. So here they are subtracted, they are in series. However, on the output side, we are the output voltage directly being fed to the feedback network. Hence, This is called a shunt configuration on the output side, and it's a series configuration on the input side. This is what we have written here. It's a series shunt configuration. The nomenclature is we write first the input side, which is series here, then we write the output side, which is shunt here, and configuration. So what we have is option C, series for input side, shunt for output side, and we obtained that closed loop gain or AF is 10. So option C is the correct option, and yeah, that's all. Thank you for listening.